A computer can be pictures. In fact, the images you are seeing now were produced this way. The computer deals with a mathematical model. The resulting output describes events in terms of time and space, and this information may be translated to a visual image on a cathode ray tube and recorded by the motion picture camera. This film has been made from a selection of scenes representing the work of a number of people interested in the technique. Selections were made to illustrate some of the distinctive advantages of computer animation. They will perhaps suggest an even wider range of possibilities for the future. Most of our knowledge comes from observation of the real world. This is flowing water, one of the examples from nature, which is complex and hard to understand, and still under study. Here is an experiment under careful control. Flow is made visible by hydrogen bubbles produced by electrolysis. The boundary conditions are relatively simple. Here is the experiment in operation. The streamline pattern may be readily made visible, and the direction of flow may be measured. And here, the velocity over time can be seen and measured accurately. Mathematical formulations for such events have been made. Expressed in computer language, these can simulate nature. Here are computer-produced versions of the flow. From the results of computation on the mathematical model, the computer can provide the basis for a display of more complex information as easily as it can show a single streamline. We may have a visual presentation of a single velocity vector, or just as easily, a number of vectors across the channel. We may have pressure readouts at any desired number of fixed points. Or, and here we go beyond our experimental capabilities, the variation in pressure as we follow an elemental volume through the channel. Already, in many cases, computer animation shows clear economic advantages over other techniques. Have you ever wondered how life would be in a planetary system in which gravitational forces varied as the cube of the distance rather than as the inverse square? This may give you some idea. We can duplicate an experiment, improve on its instrumentation, model a physical situation where an experiment is not feasible, or with equal ease, display the happenings in a non-existent world, as we are doing here. It is just as easy to program and display random events. Here we see tangents to a circle added at random angles. There are also aesthetic design possibilities in which the computer is capable of either following a most elaborate program or of improvising from very general instructions. Here is the simulated cross-section of a square steel bar. At time t equals 0, a pressure impulse was applied at the outside surface. The film is demonstrating the subsequent motion of interior points. Errors accumulate because of the finite grid size, time intervals, and round-off approximations. Obviously, our model leaves something to be desired for predictions very far into the future. Finally, the computer says, that does not compute. Computed as a forecast from measured initial conditions, extrapolated over a 66-day period. You are viewing a 22-day segment. The time scale appears by days in the upper right-hand corner, and the sun's position is plotted as the clockwise rotation of the flickering dot on the periphery. Alphanumeric characters may be produced as a sequence of short line segments, or directly from an electronic stencil, as in the monoscope or charactron tubes incorporated in the printer, the so-called character mode. Just as we can compress time, we can expand it, as in this computed propagation of shock wave pressure in an elastic medium stressed beyond the elastic limits. The event occurs in a small fraction of a second. Shown here is the escape of water under a newly opened sluice gate. It involves the solution of a finite difference Poisson's equation. This problem might require 20 to 60 minutes of computer time. Other problems, only a few seconds. Here is a sequence made as an educational experiment, designed to visualize an abstract concept. This was made for students of electrical engineering. The flexibility inherent in this computer-generated representation inspired the author to attempt a visual presentation which would stand on its own merits, without the need for either titles or soundtrack. The author first created an appropriate set of basic instructions. By the use of relatively simple subroutines, it was possible to achieve considerably greater levels of complexity. Complex movement and rearrangement of the elements in the pictures, which would be extraordinarily difficult and expensive for conventional frame-by-frame manual rendition. It was even easier and less expensive in this subsequent film made for the instruction of physics students to use the same routines in explaining certain facets of polarization in electromagnetic radiation. In the future, standardization of techniques will allow the building of libraries of basic routines to assist programmers in many fields. This Earth-Moon system shows the function of subroutines for control and placement of the image. Notice that when the pattern goes off the screen, we seem to back away and then pan to the left in order to keep the larger circle centered. This description is not in computer language. The computer sees only a series of short line segments one at a time. Look closely and you can see how the individual line segments are being added from a point-by-point description from the computer. In this man-computer interaction lies the need for computer programs, routines and subroutines, the software implementation, the real essence of the technique of computer animation. The use of perspective adds another dimension to computer animated films. In this computer-simulated carrier landing sequence, a mechanical plotter was the display device. Successive projections of the carrier were photographed. The aircraft cockpit was a fixed mask. Any still portion of a picture can be optically multiplexed into the camera. Of interest here is the ability to intersperse the appearance of inappropriate glide paths along with the correct approach. This would be a bit awkward in a real-life situation. In many cases, computer simulation can go well beyond our experimental limitations. We can instruct the computer to project an object as viewed from any desired point in three-dimensional space. Then we can choose a scale factor and have it change with time. This gives us attitude and distance, complete control over this kind of animation. Now, let's make one last perfect landing. A somewhat more abstract but still dramatic illustration of the angle of view or position in space presentation is found in this view. A fundamental and the successive addition of the first 8 odd harmonics of a square wave. We see here two slightly different views of the same figure, produced originally for three-dimensional projection. Without special optics, you might need loose eyeballs to see the 3D effect, but you can observe that the two projections are from slightly different angles. Computer-generated rotation on 3 axes allows any desired view to be projected. Here is a simulation of gyro stabilization of an orbiting satellite. Elapsed time is shown in the upper right, and the position of the gyros between stops is displayed on the front edge or face of the figure. In addition to providing perspective, the computer has been instructed to remove lines representing hidden edges so that the object appears to be solid rather than a wireframe model. This kind of display complicates the program and requires increased computer time. Here is another way of communicating with the computer. Notice the instruction panel used by the left hand and the light pen with its corresponding cross on the screen. In this case, the light pen may say, find the end of that line, it's around here somewhere. It may identify an exact point, or it may say, follow me. While not computer animation in the film production sense, This excerpt from an early sketchpad demonstration is of historical interest and does illustrate some online interaction possibilities. The producer is showing the computer what to do rather than telling it, and he needs to show it only in a rather general way. A good example of the flexibility available in this technique is illustrated in the demonstration. In drawing a circle, or segment of a circle, the computer is given the location of the center of the circle and its radius. Then the computer fills in the required arc as the light pen indicates the angle to be included. If too large an arc is drawn, it may be erased. The circle may be drawn in either direction. And when we have finally decided just what we want, that configuration may be retained and all intermediate fumbling forgotten. Here is a different technique by which the picture is presented in terms of brightness on an element-by-element basis. With a quantized grayscale, such a picture may be described in terms of binary digits, just as the Mariner pictures of Mars were returned to Earth as a sequence of zeros and ones. This kind of representation is readily compatible with a digital computer. In the present scene, 4 shades of gray and definition corresponding to only 80 horizontal lines is used for illustration. In practice, much higher definition would be usual. For typical movies, it would be laborious to describe each movie frame by its individual elements. Program routines and subroutines make relatively simple instructions feasible. Such a computer language has been developed, and entire movies produced in this way. In principle, any picture or motion picture could be so described. While our present television signals are analog rather than digital, we are beginning to use some digital methods for speech transmissions, and the digital recording and handling of pictorial information will very likely be of increasing interest. Here is the final sample, combining the pictorial work of an artist, a bouncing ball from the computer, and electronically produced computer-programmed sound.